In choosing a science fair topic, I chose a field particularly close to my heart, and that's women's health. Specifically, I focused on toxic shock syndrome, which is a disease that kills primarily young, healthy women each year, seemingly without warning. Now, since its discovery in the 1970s and 80s, toxic shock syndrome has been intrinsically linked to tampon usage during menstruation. It was originally thought that these super absorbent tampons create a contained environment in which bacteria can thrive and produce levels of toxin high enough to trigger the onset of toxic shock syndrome. With more recent studies in recent years, we realized that that may not be the only factor, and that environmental air exposure has a lot to do with the development of toxic shock syndrome. Now, why is this? Well, toxic shock syndrome is caused by the production of a pyogenic exotoxin, TSST1, by certain strains of Staphylococcus aureus. Staphylococcus needs lots of oxygen and a nice environment to grow and thrive, and this TSST1 is best produced when oxygen and carbon dioxide are present. That being said, it leads to reasoning that increased air exposure into the vaginal environment puts one at an increased risk for not only developing high levels of Staphylococcus aureus, but also high levels of TSST1 and therefore a greater risk for developing toxic shock syndrome. In my experiment, I focus on this environmental air exposure through the process of the tampon change, isolating that as the variable of interest to see whether increased tampon changes throughout the day put one at a greater risk for higher levels of Staphylococcus in the vaginal environment and higher risk for developing toxic shock syndrome. In terms of experimentation, I chose to simulate the vaginal environment in a test tube using a solution of BHI broth, which is a brain-heart infusion broth. Now, this is a bacterial medium that is meant to demonstrate how bacteria would grow in a human environment. In addition to 40 ml of BHI broth, I added 100 microliters of a rehydrated Staphylococcus epidermidis sample. This would mimic the growth of Staph A in a real vaginal environment. To manipulate the level of air exposure, I had sterilized cotton halves of tampons, which were introduced at regular intervals according to the experimental schedule, and also, during the tampon change, I would uncap the airtight test tube to allow air to flow in as would happen in real life. After the 8-hour trial, I interpreted the results of my experiment using a spectrophotometer. Now, I ran a set of spectrophotometry data right after the end of the 8 hours, and one 48 hours after the experimental period, in which time I allowed each tube to sit in an incubator at 37 degrees Celsius, as it had done during the experiment, which would mimic the human environment and allow the Staphylococcus to really take off and grow. I should mention that during this 48-hour incubation after the trial, all tubes remained sealed so that there was no additional air exposure, just what had occurred during the experimental process. Now, the initial spectrophotometry results from after the 8 hours showed virtually no difference, which is to be expected as the Staphylococcus has not had time to really incubate and grow and cause a difference in the levels. After the 48-hour incubation period, however, there is a noticeable difference between the trial groups. Additionally, I plated the data from all of the test tubes to find a rough growth estimate and to do a colony count. Unfortunately, the bacteria by that point was so highly concentrated in the solutions that a simple C-streak was not enough to separate the bacteria enough to get a firm colony count. Really, the growth overwhelmed the plates, and so if I were to repeat this experiment, we would have to dilute the solutions and make sure that we used a different streaking method to separate the colonies and create a growth environment that would be conducive to actual counting. As you can see, the level of staphylococcal growth is positively related to the number of tampon changes and therefore also the amount of environmental air exposure that the tubes received. The tubes at 2-hour changes had dramatically more staphylococcal growth than those at 4-hour and those at 8-hour. In terms of actual significance, running a student's t-test showed us that the positive and negative controls had significant difference, which is good. That means that the experiment is working as it should and that we can believe these results. And also that there is significant difference between the 2-hour and the negative, which shows that the simple air exposure from a tampon change was enough to cause an increase in staphylococcal growth over a sample that had no exposure to air. Now, as this was using high school spectrophotometry equipment, there's always going to be some error, and so adjusting my data for outliers and reconfiguring the statistics, I see significance between all of the experimental trials. The only non-significant data was between the 8-hour and the negative, which is interesting because that means that the simple air exposure from one tampon being introduced into the solution is not enough to cause a significant increase in staphylococcal growth. Now, in the real world, you can think of this as the air introduced by one tampon alone is not enough to put you at an increased risk for developing high concentrations of Staphylococcus aureus in the vaginal environment. It's that repeated change that really increases the concentration of bacteria and therefore the risk of producing high levels of TSST1. Now, looking at the data and the significance, it is seen that the hypothesis is supported, that increased environmental air exposure really does increase the concentration of staphylococcal growth in this simulated vaginal environment. Now, what does that mean in the real world? Well, it means that increased tampon changes, really frequent throughout the day, puts you at more of a risk for developing high levels of Staphylococcus A in the vaginal environment, and more of a risk for, therefore, producing TSST1 at levels that could lead to toxic shock syndrome. When deciding to simulate the vaginal environment in a test tube and then seeing how that applies to the experiment, there are some considerations that were made that I feel lend itself to the lifelike nature of this experiment. For one, when a tampon half was inserted into the experimental test tubes and taken out, it took with it some measure of the liquid inside the test tube. Normally, in a purely experimental basis, this could be cause for concern, but in this case it actually more accurately represents the vaginal environment, as when you take out a tampon, you are taking out some volume of blood and liquid mucosa from the environment. That being said, when you look at the experimental data with the multiple changes of tampons, that dramatic increase is coming from a smaller volume of liquid, which really lends itself to the idea that the environmental air exposure is dramatically increasing the staphylococcal growth. Now, why do I say that? Well, when you take the tampon out, of course you're taking with it that liquid in the tampon, as well as whatever staphylococcal growth might have taken to the outside of the cotton. So when you remove that, the end solution still had levels of Staphylococcus aureus that were significantly higher than the trials without as many tampon changes. And so that just lends itself to the validity of the idea that environmental air exposure can dramatically affect the concentrations of bacteria in the simulated vaginal environment. Additionally, in testing, there was concern that particulate matter from the cotton tampon would interfere with spectrophotometry results, but that 48-hour incubation period allowed any residual cotton to really settle to the bottom, and results were taken purely from the top layer of the test tube just to make sure that any cloudiness in the liquid is really coming from staphylococcal particulate matter, not cotton particulate matter. In the future, to refine my experiment, I would look at refining my testing methods. Labs have developed an ELISA test for the TSST1 exotoxin, and had I used a strain of Staphylococcus aureus that has in fact produced TSST1, that would have allowed me to see what the effect of environmental air exposure actually is on the TSST1 production. As I mentioned earlier, TSST1 production is not affected only by oxygen or only by carbon dioxide. It's that mixture of environmental air that really seems to lend itself to the production of the exotoxin. So an ELISA test would be helpful there. Also, concentration of Staphylococcus aureus might be better determined by a dry cell weight from each sample, not necessarily just spectrophotometry. And as I mentioned earlier, refining the plating method could lead to a more accurate colony count as well. Thank you for your time and for listening to my experiment. This whole goal of the process was really to find out more about a topic in women's health that hasn't had much attention since those initial shocking trials in the 1970s and 1980s. I hope by putting this information out there, it allows women to better understand the biological processes behind this particularly fearsome disease, and to better understand what puts them at risk and how to avoid it. Thank you.